So in the last class, we talked about overfitting, and to avoid overfitting, we have seen one of the strategy, validation and cross-fold validation. So what is overfitting? Overfitting is performing accurately on training data and performing poorly on test data. So if you plot a graph, number of epochs and the loss on x-axis and number of epochs on the x-axis and loss on y-axis, your training data, your accuracy, training data, when you're working with training data, and initially the loss will decrease and then this will be the phenomenon. And the same data, the same model, when you test with your test data, initially the loss may increase, but then the test error will increase. So high performance on training data and poor performance or on test data or unseen data. That means this is error in generalization. Our model is unable to perform well when it is tested with the generalization. So what is the reason for this? High variance and low bias. This is overfitting. And what is underfitting? Underfitting is high bias and low high bias and low variance. So what is the strategy to mitigate, to avoid this phenomena is known as regularization. So we are adding norm penalties. So in the last class, I introduced you L1 norm and L2 norm and the penalties. So what is the point here? The point here is we are adding penalty. So let us say our cost function, maybe it is mean square error. If it is a regression problem, mean square or mean absolute error. If it is classification problem, binary cross entropy, binary classification, categorical cross entropy, categorical or multi-class classification, then KL divergence, all this regularization cost functions. So earlier we used to indicate it by E, but this textbook and Goodfellow textbook, they represent it by J. And the parameter is theta, and we are given with X and Y. So theta, here it is what we are done with. We are doing it with the weights and bias. That's what we are computing. So what we are doing in regularization is, so instead of writing J theta, I can write JWB X comma Y, X comma Y. And one more point we have also made it clear that in regularization we are not touching biases. We are regularizing only weights. Bias is left because bias is a single term, uh, untouched or unregularized. We are not regularizing bias, we are regularizing only the weights. So instead of writing j theta, I will prefer to write j w given the x and y is calculated, it is a computed after regularization is unregularized cost function, unregularized cost function plus the penalty. And there is we define a hyperparameter called regularization parameter and your penalty function omega of theta. So what is alpha here? Alpha is a hyperparameter which we can call regularization parameter. Regularization parameter. So if alpha is high, you are adding more high penalty, more penalty. If alpha is 0, it is left unregularized. So even the cost function is same after the regularization. Now let us look at what is L2 regularization. I already told you L2 regularization is also called what is that? Ridge regression, and it is also called as techno regularization. And in the last lecture, when I spoke about L1 and L2 norm, we identified that L2 norm deals with the squared penalty. So here in L2 norm, we define this omega of theta or W. We can write W, right? Instead of omega of theta can be defined as half the weights square, the squared penalty, squared penalty. So now our equation for the cost function after the regularization, it becomes j bar after the regularization, which is function weight we are calculating. We are given with input x and the label y is existing cost function y plus alpha, that was hyperparameter which determines the weightage of regularization, and square, because W is a matrix, rather than writing square we can also write W transpose and W. And you know that we need gradient to be minimum. If you remember the perceptron learning, we calculated the gradient of the cost function delta of j or del w of j, and we calculated the weight update as w dash or w nu or w star is equal to w minus learning rate eta into the gradient of j. This was the weight update without any regularization term. This we know it already. This is weight update term. What is our gradient? Change in the error when we change the weight. Weight update rule without regularization. Now, let us call this as maybe equation 1. From the equation 1, let us calculate the gradient. What is gradient? Partial derivative with respect to the weights. So, is the existing gradient plus the derivative of this term. Alpha is constant, w square derivative is 2w, 2.5 gets cancelled, so we got it as alpha w, alpha w. And now let us calculate the weight update term. So the new weight, which we can call as square w star, is calculated with w minus learning rate eta into the new gradient. What is new gradient? Delta j bar, or if you want we can write that in full, x and y, and substituting that w minus learning rate into, this is alpha w plus, from equation 2, this we can call 3, and plus delta existing gradient. So simplifying this is equal to w common, you can take 1 minus learning rate into regularization parameter plus, or rather it is minus learning rate into j cost function. Now compare this equation without regularization and compare this with regularization. What difference you find? Here this term is same, right? This term is same. This term is same. This term is same. The only thing is, earlier it used w minus, now it is using w into 1 minus and neta alpha. Earlier we were subtracting this learning rate into gradient from W. Now we are subtracting this learning rate into gradient from weight which is multiplied by a factor which is less than 1. That means in regularization, you are reducing, you are shrinking the weights. By L2 regularization or even in L1 also, in L2 regularization, we are reducing or shrinking the weights. Shrinking the weights. That's why this L2 regularization, which is also called ridge regression, which is also called techno regularization, is also known as called as weight decay, because the weights are being reduced. That means by regularization, what we are doing is we are penalizing the gradient. So earlier, suppose this is your model without regularization. By penalizing, we are developing another line which has which has less slope, but it may not fit the training data as perfectly as our earlier model, but it will ultimately fit the testing data, not perfectly, but to much extent. So this L2 regularization is shrinking the weights, but remember, it is not making them zero. Whereas in L1 regularization, it makes some weights as zero. This is the mathematical intuition behind the L2 regularization. And what we can see from here, weight is being reduced. Weight is being reduced. And if it is linear regression, suppose you are dealing with linear regression. In linear regression, we'll be talking about mean square error. What is mean square error? Predicted y minus actual y minus predicted y. So wx minus 2 transpose to wx minus. To this, we are adding a term of alpha w square or w transpose into w. So when this gradient is equal to 0, we'll calculate the weights. And there is one more expansion, even Taylor's expansion. From that, we can deduce that when it is reducing weight, it is reducing in the direction of eigenvector. What is eigenvector? It is a direction which will not change even after transformation or translation. So, let me show you the diagram. The L2 regularization, which is a squared. Suppose this is our W star without regularization, and the contour values are this one. Sorry, they should not intersect each other. And our L2 family is here. L2 family is a spherical. X1 square plus x2 square is less than r square. and they intersect here. So that means earlier without regularization, this was the optimum point. Now it has been shrinked, drawn towards the horizon. Weight has been reduced, but it is not made zero. So this is the contour plot, and this is the geometrical interpretation, intuition. This is without regularization. This is L2 regularization.